Dear friends, in this short video, I will simply emphasize and remind you of some well-known properties of polynomials modular prime number. So let's start from a prime number, p. And what is a polynomial modular prime number? Well, consider the set of all remainders modular p, which we denote by z over p z, which as a set is equal to 0, 1, 2, and so on, p minus 1, but these are only representatives of elements of this set. And we know that there are arithmetic operations on this set, such as addition, multiplication, subtraction, and even division, or it may be denoted as two dots. And this set of remainders with corresponding operations form a field. Well, this is a well-known fact. And let's just feel that it is obvious that all field properties for addition, multiplication, subtraction obviously hold, and field properties concerning division hold because some time before we proved that for every a in this set except for 0, there exists a b in this set. B will also not be equal to 0, but it doesn't matter right now, such that a multiplied by b are congruent to 1 modulo p, which means that a multiplied by b is equal to 1 according to this operation, these operations in this field. So having this field, we can consider the set of polynomials with coefficients in this field, so z over pz, and let's denote the variable of polynomial by x. And since this is a field, then this set of polynomials also having operations of addition, multiplication, subtraction, and division satisfies, the set of polynomials according to this operation satisfies some standard properties. Well, first let's spend just half a minute talking about what does it mean according to these operations in the sense of modulo p. Well, this means that all the coefficients of these polynomials are in this set over here. And when adding one polynomial to another or multiplying two polynomials, we must reduce all of obtained integer coefficients to those of this set. Just reduce them modulo p. So arithmetics among coefficients is modulo p, whereas the degree of such a polynomial can be in arbitrary integer number, well, arbitrary positive integer number, or 0. So what are these well-known properties? Of course, this set of polynomials is a Euclidean ring. So we have the property of unique prime factorization, where a prime polynomial is an irreducible polynomial. Prime uniqueness of prime factorization. Well, I just write factorization to be short. The second property quite well-known natural property for polynomials over a field, that the number of roots of such a polynomial cannot exceed the degree of the polynomial. So if we have a polynomial of degree n, then the number of roots of this polynomial is not greater than n. And finally, the third property, which is also well known, but maybe not so well known as the previous two. The third property is the following. If we have two polynomials, and we know that roots of the first one are the same as roots of the second one, well, if we have roots that are not simple roots, but repeating roots, then the frequency of their being here must be equal to the frequency of being here. So if the set of roots coincide, then these two polynomials are proportional, which means that there exists an element of the field such that one of the polynomials is equal to this element multiplied by the second polynomial. Actually, the second polynomial multiplied by this element. So these three properties are proved in many algebra textbooks. We'll not spend time now to prove them, but we will use them. So we spent these several minutes just to recall the properties we will need in the future.